we thought just to wait for a couple of minutes because people finished after almost 4:15, so we wanted to give you a couple of minutes as a break, and then I think we just warm up till the people come back from the break. And today's topic is something that I think everyone might agree that it's very vital and very important for the country, and also not only for Egypt, but it's for the whole region. And the region, when I say the region, I personally like to start by the African region and then the Arab region. We are today presenting you a specific project, so it's not a theoretical type of talk or presentations as we normally do. Now I feel more comfortable by like moving. So our topic is Water-Energy-Food Nexus, and this is a platform that we're trying to develop, a knowledge platform we're trying to develop between Egyptian universities, research centers, industry, and some European universities, as I will show you later on. But I would like to start by some issues like the water scarcity. I think we all know that water scarcity is affecting many countries in the region, in Africa, in Egypt, and Middle East. And we are all now talking about sustainable development. And sustainable development is the development that satisfies our needs and respect and give the next generation also the opportunity to satisfy their needs and give them the resources available, which means that when we use a river Nile, we have to leave it for the next generation as we received it, with the same water quality and the same water quantity as well. So this is the very simple definition of sustainable development. I'm personally very happy to see that Egypt is moving, in my opinion, in a good direction regarding sustainable development by having this Egypt 2030 vision for sustainable development, which is in line with what's happening globally, like the Millennium Development Goals, which already were to be implemented till 2015, and now we are dealing with the 17 Sustainable Development Goals, or the SDGs, to be implemented by the year 2030, which is matching exactly our Egyptian vision for sustainable development 2030. So water is playing a very significant role in all the Millennium and Sustainable Development Goals. You find water is playing a significant role, and the issue is that we are in Egypt, we are below the poverty line, and the poverty line is 1,000 cubic meter per person per year, and we are now 670, and I think we will be also dropping under this number in the coming couple of years. This is just the Arab countries or the Middle Eastern countries, and here you see this is 1,000 cubic meter per person per year, and here is y-axis, and on the x-axis you see the different Arab countries, and you just draw the poverty line, then you will see all what's under this poverty line are countries who are poor in terms of water resources. So this is a situation in the Arab countries, Egypt, Syria, Oman, Tunisia, etc., with a very, very little and very few exceptions for some countries who are not under the water poverty line. We always talk about water in terms of quantity, in terms of when I ask you what do you think about a certain product, sometimes you really don't know that there is what's called hidden water in this product. What does it mean? It means when we talk about CO2 emission, for example, the CO2 footprint may be more popular than the water footprint. Then you say, okay, when I travel from point A to point B using my car, I'm producing certain amount of CO2. But if I ask you the water footprint, then it means if you are eating an orange, then you can calculate all the water used, not inside the orange, but the water used for irrigating the orange, harvesting, packing, washing, whatever, till it reaches you how much water it was used for. And this is simply the water footprint. Just to give you an idea, and with some simple examples, this very small, tiny cup of coffee, it needs 140 liters of water to reach you. And this piece of beef, which is 300 grams, needs 4,500 liters of water, and this is what we call the water footprint. So important for my presentation, at least, to know that we have blue, green, and gray. And the blue is the water that's coming on the surface, is used for a certain product, but it's surface water or groundwater. The green one is a rainfall, and the gray one, of course, is the one is polluted, or the water polluted to produce a certain product. To go for more examples, and I think today I want you to see the issue with the Nile Basin countries in a different way. We used to discuss it about water amount that's reaching Egypt, or the water amount that's released starting from Ethiopia, divided between Egypt and Sudan, and then we're all the time repeating the same numbers, the same quantity, etc. Today I would like you to see it in a different way. Today we would like to put the water footprint factor in the equation and see how we can see the problem in the Nile Basin countries using different glasses. And that's exactly what I'm not hearing in the negotiation or in a discussion or in the media or in any place. I don't know why, but these information are basics for the water experts that I see in the room. I know them and I know some faces. They know that. This is basic. This is nothing advanced and not the result of research. But it's not in the discussion and it's not in the equation. So Egypt is receiving less than 3% of the rainfall hitting the Nile Basin countries. And this is what we call the blue water. So if they have 2,000 billion cubic meter, we are receiving 55.5. It's not their fault and it's not our fault. I'm just giving you some facts. So if we go to the discussion between our brothers and neighbors in Ethiopia, let us see this x-axis is million cubic meter per year, and here Egypt is always this gray, and Ethiopia is the white one. So Egypt is using this amount of green water from the rainfall, and Ethiopia is using this amount. The blue one, of course, Egypt is receiving 55.5 billion cubic meter, and Ethiopia is receiving a very little amount of blue water. And the discussion is always here, in the middle, in this blue part, because everyone is discussing the shared surface water, but we are not discussing this rainfall, this green part of the equation. It's not in the discussion. And you see here, the gray, Egypt is recycling too much water, so we do really recycle a lot, and Ethiopia is not recycling, or there is no need to recycle. And if you sum up, then you come up with this conclusion at the end that Egypt is using 68 billion, and Ethiopia is using much more, not much more, but a little bit higher than Egypt. So there is a kind of fairness in the distribution. And this is not my problem, is to show that we are not taking more water than Ethiopia. It's not the point. The point is to go back to the slide saying we are receiving less than 3% of the rainfall. And here is the solution in my point of view, is to go for the rainfall and try to harvest more rainfall for the sake of satisfying all the Nile Basin countries in terms of water resources, and this is a part. Now we are moving to using water for producing hydropower. So there is a competition here. Ethiopia is claiming or saying or publishing that they're building a dam in order to use the water for producing energy. So what we call water for energy. This is going to affect Egypt that's going to use the water for energy and for food. So we started to hear water, energy, food. Okay. So that's why the international community is started to say some years ago, officially in 2009, when we think about water, we cannot separate water from food and we cannot separate water from energy. Because water is used for cooling power plants, and it's big amounts of water. Water is used for hydropower, producing energy, as I just mentioned, the example of Ethiopia. Water is also used to produce biofuel. This is a crop, agriculture product that's going to produce energy later on. So you are using water to drive your car. This is a very important equation that we need to take care of. You cannot treat or desalinate water without energy. And if desalination is expensive, it's just because of the energy used. And if desalination is cheap, because of the less energy you used in the desalination process. Water is used for food, this is clear. And all these types of products and all this supply chain needs energy at the end. So, and here is this idea, which is, in my opinion, it's a kind of bad idea, is to use food for producing energy. In this case, using maize to producing biofuel, which I will never support as a researcher. So from the previous slides, I think we now very clear that this interrelationship between energy, food, and water, it's very, very effective and very important to consider them as one equation. You cannot separate them anymore. That's why, I'm sorry for the long introduction, these all partners, they came together. They started to think of an approach how the Egyptian researchers can improve their capabilities, their skills, their infrastructure in order to do a kind of research, in order to bring these water, energy, food together. You might think it's an easy task. It's not, because I am coming from the water sector. I'm not expert in energy, but we have other people in the sector of energy. We have other people in the sector of agriculture and food. How can we work together? How can I understand a little bit of his task and he can understand a bit of my task in collaboration, of course, with different universities. So here we have Alexandria University. We have Bibliotheca Alexandrina. I don't know why it's not here, but Bibliotheca Alexandrina is a very important partner in this project. We have my university, Aachen University in Germany. We have Technical University of Graz, Politecnico di Milano, Heliopolis University. We have Cairo University, the American University in Cairo, and also Sub-Agro. It's an agriculture and food production institute in Montpellier in France. So these are the people who decided together to start bringing these three pillars or water, energy, food together in one equation. As I said before, the problem with Ethiopia can be solved in one way or the other using this concept and integrating it with the water footprint and all these objects. So what are the objectives of this initiative that we started 2 years ago? The objective is to develop a strategy. First of all, if you talk to the Ministry of Water Resources, and we have Dr. Mohammed here available with us, then they will tell you we have our strategy. And if you ask the Ministry of Energy, they have a different strategy. And if you ask the Ministry of Agriculture, they have a different strategy. And this will not help us to implement this approach that is becoming a trend, water, energy, food as one unit. So we need to help them by proposing a strategy. How can we bring all these ministers together or ministries together? And this is, of course, cannot be done without involving them, without asking them, because we're not giving ourselves as researchers the authority to tell them what to do. We just have to listen. We have to help them. We have to collaborate together. And I think it was very successful couple of workshops that we organized, and we came up with a draft strategy for Egypt that is more or less in line with the Egyptian Vision 2030 or Sustainable Development Vision for Egypt. And the second objective was about coordination body. We would like to have in each university people are coordinating this, who will be trained, who have been trained already in Europe, trained in Aachen in Germany, trained in Milano. They will be traveling to Montpellier soon to be trained on how to collaborate together. And we are main focus on the juniors of researchers. And in February 2017, we will be organizing, January, February, we will be organizing for young PhD researchers a summer school on how to deal with the issue of water, energy, food. And I invite all of you who see themselves as juniors to collaborate and participate in this summer school, or at least to apply to be part of it. And the last objective is about knowledge sharing, and this is a point that I would like to focus on it on the panel, because the project is quite big and we cannot cover all of its aspects in here. And this is a model that we are presenting. Desalination itself, it's not a sustainable technology. The way it's used today, it's not sustainable and it's not green. And what we're trying to do in this model is to try to green desalination. We try to make it more sustainable and affect or reduce or minimize the negative impacts of desalination, since we are talking about sustainability and sustainable development. So what we are using here is using solar power or solar energy for the desalination process itself, but here we are focusing more on water for irrigation. Of course, everyone knows that desalination is producing drinking water with a higher price than the normal prices we know in the normal water tap in Egypt. And now talking about using desalination for irrigation is quite crazy idea, actually, because if it's expensive to drink, how come you are going to use desalinated water for agriculture, and then you are going to produce me a kilo of tomato for 50 pounds? Then doesn't make sense. You cannot compete the river water unless you have a new technique that's going to produce water in a very low price. And that's what we are trying to do, as I will show you later on. And then we produce water for agriculture. And since this is a water that's really done after a lot of efforts, you cannot just spread it like this. You just have to use advanced technology like the one we test is a subsurface irrigation for agriculture. Desalination has two main problems. There are other problems, but the two main problems. First one is the energy, how to produce energy in a low price. Especially are not a country that you have the energy technology, or importing most of your technologies from abroad. And the second big problem is the prime. And the prime is a byproduct, the high saline water that you normally dispose in the sea, or some crazy initiatives, so not going to go in deep, they inject it in the underground water just to get rid of the prime, which is a very high saline water. What we are proposing here is a new technology for desalination. I will give some words about it later on, but Dr. Yahya is here, who's going to go in more details. And we use the prime for producing food as well, by growing a kind of species or whatever type of animals, like the Artemia, for example, the one we are trying to test now, that it lives in such high saline water, and it is a very good food for shrimps or fish later on. So we're trying to close the loop in order not to have any negative impact on the environment and not produce any byproducts and try to dispose them and affect the environment. In this case, hopefully we are able to produce a dry salt at the end. You produce food from the byproduct, and you produce food using the irrigation water that you are producing from the desalination. Part of this research is still a lab and bench scale type of experiments running between Germany, Egypt, mainly in using the labs of facilities of the American University in Cairo. Some experiments we are doing over there. Alexandria University is doing a good job also, but focusing mainly on the membrane. We are focusing on the draw solution. This is a model that we built already, and it's partially running already here. I have to skip these ones, but I'll stop here for a couple of minutes to explain you the idea that we are using without more technical details. The well-known type of desalination is the reverse osmosis. And the reverse osmosis, I see many students here. I'm sure you are aware of that. You have here the salty water, and you have on the other side the fresh water. If you leave it to the natural, then the water will be moving from the fresh side to the salty side because of the osmotic pressure. But if you practice pressure here, then you force the water to move from the salty side to the fresh side, if I'm not mistaken so far. And then, so you practice pressure here, and this pressure is the energy consumption that you are using, which is one part of the cost of the whole process. What we are doing is another issue. We, Alexandria and other researchers, we try to mix this side with chemicals, for example, to increase the osmotic pressure and then to let the water move from the left side to the right side without energy. So theoretically, with zero energy. But then you have water mixed with chemicals, then you have to separate it. So we solved one problem, so separated the water from the salt, and then we have to solve the other problem. Solving it could be by heating, and it's using energy, or solving it with the other way. But what we are doing now, and we are testing, that we are not mixing it with chemicals, we are mixing the water with fertilizers. So if we mix it with fertilizers, we increase the osmotic pressure on that side, we separate the water from the salt, and then we use it directly for irrigation. So theoretically, again theoretically, with zero energy, you do your desalination, but you are not producing water for drinking, you are producing water for irrigation. So this is the idea that we are trying to do. We have been quite successful in testing some of the local fertilizers used already in Egypt in order to do that. And we have some good publication. I think we've published already 4 or 5 papers and book chapters, etc., on that topic. And here are some of the results. It shows you that using this type, what is not reverse osmosis, it's forward osmosis, is really consuming a very, very little amount of energy. And this is the experiment. This is the bench scale experiment that we are running here. And we have already tested some fertilizers. This is the model when we design using the PV panels. And this is a real pilot implementation. This is from the other side. This is the full scale. After testing it in the lab, then we start testing in a full scale in order when we come at a certain point and we tell the government, now we are ready for implementation, then we already ready by having the prototype and we have the right model to be implemented. And here, I will stop here, let my colleagues complete. Our approach is, this is the objective of our project. That's what we want to reach, either next year or in 10 years, we never know. We have a plan, and we are doing well, at least in the desalination part. Dr. Abdelaziz, the Dean of Faculty of Engineering, Alexandria University, Dr. Yahya and his team are doing the membrane part. They are doing membrane. They are also doing forward osmosis draw solution, but they are focusing more on the membrane, and they will be presenting this later on, because the issue is, what we are trying to do is to find out which type of fertilizers and how to optimize the process. But we will be still importing this technology, importing the membrane itself. And what I think it's a very good step that at least 1 or 2 universities in Egypt are doing this in order to produce this forward membrane at the end in Egypt. And then once it's Egyptian technology, then the price will be quite cheap. So this is the role of Alexandria, will be presented later on, and here, this part of Artemia and the agriculture part is the task of Cairo University, and that's why, as I said at the beginning, it's impossible to separate between energy, water, and food people, so we have to collaborate together, and this will be presented by Dr. Ashraf, but also Dr. Rasha is going to present some great ideas for a model water-energy-food connections. This was a visit of the former prime minister to this experiment at a certain point, and these are the sources I used in my presentation here. If you are interested later on to get these sources, I will send you. Thank you very much for your attention. Now I give the floor to Professor Rasha Al-Khouri. She is the Dean of the Faculty of Engineering at Heliopolis University. Heliopolis University, she will correct me, Heliopolis University for Sustainable Development. And she is going to present also some good examples for implementing the Water-Energy-Food Nexus that I just described its background. I hope I was not too long, but I told them before the session we have to restrict to 10 minutes, and I'm sure I was exceeding the 10 minutes and no one stopped me from their side. Thank you very much for this.
Thank you very much, Dr. Hani. I'd like to welcome you all with a very small presentation about a pilot prototype that's implemented in Heliopolis University. The beauty of the project is it's trying to compile many aspects together and put them on the ground to be a model that can be implemented in many not just universities or institutions, but it could be on any other pilot scale. So when we started, we were thinking of the part of the energy, but we thought we might extend more and have something on the ground that can be applicable and can be used by students and staff and even can be productive. So this is the triangle that we've been talking about, the triangle having the water, food, and energy, and how they are interlinked together. They cannot be separated. And looking back at the strategies of the different ministries and how they are not isolated, but they are each on a separate track. But we were trying to look at the linkages between those strategies and find our way that can support the Egyptian community with applicable research. We, as researchers and academics, have to put it on the ground and say, that's what we can do. So at Heliopolis, we were looking at water from a perspective of desalination and aquaponics. And aquaponics, we mean aquaponics for fish and hydroponics as well. And this will be given shortly. Looking at food, we were looking at a greenhouse. A greenhouse that's quite different from the traditional one we know, but a greenhouse that is producing some food, some vegetables, and eatable crops. And an energy with a new technology of semi-transparent panels that can be used within the house itself, and an RO that is using the energy of the photovoltaics, not traditional energy. So if you look at the whole thing, it's not a traditional using traditional resources system, but rather an innovative system built on untraditional resources, whether energy and water. This is the part of the water that we're using reverse osmosis, as you all know, a very small unit that's Egyptian developed and can be handled small scale. The produced water is 500 part per million, so it's quite fresh water that can be used in agriculture or aquaponics. The photo shows the greenhouse. The greenhouse is topped with photovoltaic panels that are semi-transparent. The transparency is 40 to 50%, so allowing the light to go in the greenhouse, so the greenhouse can be used for cultivating crops, not as dead areas that's normally found under traditional photovoltaic panels. And you can see these are the hydroponics where we will grow the plants inside the greenhouse. We are keen to keep the temperature within the greenhouse between 28 to 24 degrees Celsius so that there is maintained weather with fans and as well the water that will be flowing into the greenhouse. This is shortly showing how the orientation is set. These 14 times 10 channels or panels for the hydroponics, showing how it's distributed. These are the hydroponics. The other part will be for the aquaponics growing fish. So these are the fish tanks. And these are clarifiers that will take the water to filters. Filters then will pass to a disgassing unit, and this water flow into hydroponics. So the same water that's coming from the RO unit will go from the fish tanks to the hydroponics to the plants being filled with fertilizers coming from the fish wastes. And then this water go in a very closed loop, again, from the hydroponics to sump and pumps, taking this water to the fish fangs after the nutrients are absorbed from the water. So the water is kind of filtered through the process to be used. So not wasting, we are maximizing the use of water, as Dr. Hani said, because water is precious. So whenever we are getting some products, the water is kind of used many times. And this water is not from any type of the traditional water, it's water from the well that comes with salination about 10,000 part per million. So these are the part that's colored, is covered with the semi-transparent panels. It's covering the part. Underneath is the plant, and the other part is with carbonated sheets, so it's covered for the production of fish and crops with a total area of 0.025 hectares and 70 cubic meters of water. So this in total is what we need for this unit, and then I'm trying to put it to just let you see how simple the system is, having just some containers, some open channels, and some units that are locally produced that we can use in our water unit system, tanks for fish, and clarifiers, and degassing tank, the 3 long hydroponic tanks, and the where the crops will be planted, and as I said, is 70 cubic meters of water. The energy units is used for the blowers, air blowers, and the water is used for the pumps and the water pump, the motor that will be used in the RO and air and passing the water from one part to another. And all this energy is not using any electricity, it's using the power produced from the transparent panels. Food production, we're talking about a fish that's normally in fresh water, it's the tilapia, and as for crops, we're talking about lettuce, basil, and okra that can be planted using this water. These are the picture of the how the fish will be in the circular tanks. This is how the plants are cropped within the long hydroponics. And if you look at this, there is no soil, so this will be the sides of the plants. These are the units that's existing in Heliopolis University, and the good part is that they are not just used for research, they are used for just educational courses undergraduate that students can go and get samples of water, test the efficiency of the panels, the orientations of the panel, comparing these panels with the traditional PV that are existing, so that these are all used and made use of within the campus. So we're just presenting the model that can be implemented elsewhere, and we're also putting it on the use of students and teaching assistants and even researchers who are interested to take a part of it, and it's on the hands of the coming PhD summer school to be part of the implemented research. This is the inside of the greenhouse. These are the fish tanks. And then this draws us back to the triangle of water, food, and energy, with the triangle of research, innovation, and education. So education, yes, they are used for educational purposes. They are used for part of the labs. They are used for research, and they are used for a very innovative solution comparing this type of energy, which was the main starting point for Heliopolis University, the renewable energy systems, and as well as the implementation of water desalination for the use of organic fish and organic plantation of crops, and the real monitoring system that are located within the greenhouse and to our labs. And these are the educational labs that came from within the project for the need of the pilot and for the use of the students. The Smart Grid Professional Lab, the Wind Professional kits, and the advanced photovoltaics training system that's comparing the different types, and as well as the big water quality monitoring lab. That's the processes that have been through. Conclusion about them: that we're doing the assessment, we're doing the monitoring, we're doing the comparison with the traditional systems for energy. We're doing part of our teaching applications and systems based on what we have on the ground, and not only this, but Heliopolis is full of pilots. Whenever there is a project, we take the chance of having a pilot on the ground. And the idea of a new full new greenhouse with photovoltaics on top and aquaponics, hydroponics, and a very closed system saving every drop of water and desalinating the well water, not using any sort of traditional water. And then we're starting the process of the monitoring of climate changes happening, the water quality changes that would emerge from using a case like this, and then thinking of when having an extra energy, connecting it to the grid and getting more money. So that would be very tempting to implementation. And of course, the coming phase will be producing fish, biofish, and plants that would be available to the market, and hopefully that will be commercialized. And then looking at other aspects like the social, environmental, health aspects related to the issues we've been discussing, and linking the Trinex experiments to further research that you young researchers can follow up and take upon. I'd like to thank first my colleagues who helped me putting this presentation together and showing you the pictures of what's on the ground. Looking forward to see you, and I'd like to thank the Erasmus Plus, the Tempest, and Dr. Hani Swalem for big support to have these things on the ground as we speak, and then have it implemented elsewhere. Would be pleased to see it not only in Heliopolis, but all over Egypt. Thank you.
Thank you very much, Dr. Rasha, and I can see also you have even started things new that I was not aware of. So this was also another example of integrated the three pillars that we said before or explained before, and now I think we will be focusing more on agriculture and aquaculture, which is something that I personally feel we need to do a lot more in Egypt. I think this sector in Egypt is lagging behind many other sectors, so I think water is even more advanced than agriculture. But we do have very good researchers here in Egypt, and I think Dr. Ashraf is one of the people with Dr. Ashraf Al-Arnaouti and the others from Cairo University. They are doing a good job, and I think now it's, I leave the floor for Dr. Ashraf Sallouma to explain us how he is tackling the food and the agriculture part of the Water-Energy-Food Nexus. You have the floor.
So my presentation under title Improving Sustainability of Agriculture and Aquaculture System in Egypt. The first, we need to know what is the current situation of the production system of aquaculture and agriculture system in Egypt. And first, for agriculture, the most problem is related to the self-sufficiency of some crops in Egypt. That we have problem with some crops that the self-sufficiency is less than 50%. Like grains or oils, crops for oils, and this is this is the most important problem related to agriculture system in Egypt, and we will talk about it and to find some solution. And when we talk about aquaculture, the problem may be bigger because, yes, we are the second producer for tilapia after China, but this production of tilapia is came from unsustainable production system, because this system is semi-intensive system that the main source of water for this system is agricultural drainage water. And we know what's the profile of this water. And this means that the water quality itself is very low. And this system also, the production of this the average of production of this system is average of 1 kilogram per meter. So it's very low production. and it's consumed from 10 to 27 meter of water, cubic meter of water per each kilogram of fish. Of course, if you discuss this with the farmer, he told you that I am not consuming fresh water for the farming fish. I am consuming agricultural drainage water. But according to the government strategy in the future, that they will treat this agricultural drainage. So if they treat this agriculture, the question now, they will give the farmer to product for the farmer who produced fish, they will give him treated water. This is the question. So this is unsustainable system. And here, after we show our situation in the production of aquaculture and agriculture, we can characterize the problem, assuming that the water which will used for agriculture and aquaculture is from fresh water, and we call it freshwater model. Under freshwater model means that the only water that will be used is fresh water. We have problem related to food insecurity and water shortage and land shortage. So what is the solution? The solution is to increase the production of agriculture and aquaculture, but under intensive system, and improve the water utilization. That means that decrease the water use in agriculture and agriculture. And of course, there is no solution that we have only arid land to use. And this mean, this equal that one of these, if we merge of this solution, the government start to expand the agriculture area with more 1.5 million acres. Our agriculture land now it's around 8 million, and this is a great work. This is a great project. We support it, and also we recommend to link between the agriculture and aquaculture, which we called it agriculture integration system, because this system will save the water and will increase the sustainability of the system. But here, when we talk with the future and expanding the agricultural land with 1.5 million of acres, we have to ask this question. This is an important question. What is the policy or what is the strategy that the government will select the species for this new land? This question means we are going to select the species according to the strategy of self-sufficiency of food or the strategy of getting more foreign currency and to get food, to improve the food security, but with indirect way. This question is very important because now we start the first phase of this project, this big project. So I think that the government select the self-sufficiency strategy. And this is very dangerous because we think that in our, from economically and from sustainability point of view, we think that both policies are important. But this is not only and both policies are to be considered, but not only the policies. We need also to take in our account more consideration related to what we select of this species to be cultivated is that this species must be with low energy footprint and low water footprint. I mean that we can cultivate or select species to cultivate that we can import it and we get foreign currency that we can export it and can import the self-sufficiency crops that we need. So the most important in this project is that how we can select these species that we will cultivate. Okay, now we will talk about the second characterization of the problem, assuming that not all the water that we will use is fresh water. I mean that there is some agriculture area or some new communities that the government going to implement. It will be in the area that there is no fresh water. So the questions now, how we can utilize from the saline water. So now we need to use the saline water and to also to use renewable energy. So this is the concept of Trinex project, that we need to help the government in the idea that they have to focus in the coastal and desert agriculture and aquaculture system, which means that in coastal and subcoastal area or in the desert area, the source of the water will be seawater, or it will be brackish water, that it can be desalinated, and the product of the desalination will be one of the three of brine or low salinity or drinking water. And this is our task in Cairo University, is to how utilized from these three sources. I mean, in the case of the source, it will be brine, and this is high level of salinity, near to 100 BVT. So the only solution to utilize from this brine is to cultivate Artemia. And this is one of the small crustacea that can be fed to fish or shrimp in early stage, because they cannot feed on diet. And in the case of the low salinity, we can use this low salinity in saline aquaponic, not freshwater aquaponic, saline aquaponic, that we need to also, it can be used in bifloc system. This system means that you can utilize the low salinity or seawater in farming fish in a zero exchange system, that we can treat the water inside the system. We didn't need biological filter. So this is zero exchange, because the problem is that we cannot use the low salinity or the seawater directly in the land, because this is unsustainability way. That this means that it will be increase the salinity of the land, and it would be affect the underground water. And also, we can, and this will be the food for the new community that will be in the desert and in the coastal and subcoastal area. So, in the saline model, the first important is which species that will be used, because now we talk about low salinity or seawater. There is many species groups or fish that with high tolerance of salinity. But this tolerance, tolerance of salinity tolerance, it determined in soil conditions. But we know we need to develop a soilless system. So not all these species can be used in the soilless system. But for example, we have two important groups that can be used in soilless system. It's Salicornia and the quinoa. And quinoa is very important because it's alternative to the grains, the famous grains. It's because of it's and the FAO named it as a mother of seed. And quinoa, it's high. It had many advantages, like it's free gluten and rich in fiber, and it's high protein content. So it's very important because it can be alternative source for the famous grains. And also the amino acid is rich. And the other species that can be, which we can use in the soilless system is Salicornia. And Salicornia can tolerate high level of salinity, and it's one of the cash crops that can be exported. And this is the Salicornia field, but this is not in Egypt. This is in Eritrea, that they used the seawater directly to irrigate the Salicornia. This is here they are happy that they have good yield crop, but the problem here, this is not sustainable cultivation because they directly use the seawater in farming Salicornia. So in Cairo University team will be responsible in developing saline aquaponic. And the first experiment scale will be test some selected species that with high tolerance is recommended as a high tolerance to saline, but this is determined in the under soil condition. We will test it under aquaponic system. And we will select from these species the species that we will give high performance. We select it to test it under commercial scale of saline aquaponic. This slide show the economically the expected performance and the marketing of the Salicornia and quinoa. And if there is, if the project will be extended, we will test the fourth generation of aquaponic, which is we call the Japanese style, which we named aquaponic factory. This system, the size of the system is the same as a football field. It's about 7,000 meters, and this produces daily 10,000 head of lettuce per day. So if there is a time on the project, we will test this fourth generation of aquaponic. Thank you.
Thank you very much, Dr. Ashraf, for the quite long presentation. But I think till you start your presentation, Dr. Yahya. Dr. Yahya is a professor at the Faculty of Engineering, Alexandria University, and he's going to cover the part of desalination and more, not on the draw solution and the fertilizers used, but more on the membrane itself. That this is, I hope it's a kind of dream for us as researchers to produce an Egyptian membrane, because once you have an Egyptian desalination technology will be cheaper, and especially if you're using solar energy, then there will be really hope. And if you follow the agriculture methodologies presented by Dr. Ashraf, and I think it makes sense to produce food from desalinated water at that time. So, Dr. Yahya, you have the floor. And you have also 10 minutes.
Thank you, Dr. Hani. I would like first to thank Bibliotheca Alexandrina for hosting this session. I would like also to thank all the Trinex people that are working in this project. And, well, 2 notes. I'll try to cut it short, since I'm from Alexandria and the conference is in our city, so my goals is counted as 1. The goals of the visitors counted as double. And second note, for my students who are here, yeah, you can count this and question in the exam. Well, I'm going to talk about the membrane and the forward osmosis modules that we are working on in the team of Alexandria University. So, what we are trying to do, what we are going to do is, first of all, build a membrane that is made in Egypt and that will cut the price of the system very well. It's going to cut it by a lot of money. And it's going to let us know what the knowledge and the know-how of how to make the membrane. The second part is that we are going to study the application of the forward osmosis, how we can use it in desalination, in treating of wastewater, agricultural wastewater, all of this. What we focused on is composite polymeric membranes, which was made in a small sample with a small module for forward osmosis. Yeah, so that's how it was made. It was made from polysulfone and polypyridol and some other chemicals. It's made on 2 layers. The active layer, which is the one that is responsible for letting the water pass and rejecting the solutes. And that's the process how to make it. You add the polymers, materials together, the chemicals together, and then you start to cast it and roll it to make it like a film. And that's the module for the FO. It's a small module where you can let with pipes coming in for the feed solution and for the draw solution, where you can pass the 2 liquids and then measure the concentration after it has passed in it. And that's how we fix the membrane. So what we did study is, 2 types of membrane we used, or we made 2 types of membrane. One is the thin film composite membrane, TFC, and then thin film nanocomposite, which is we doped the membrane with some zeolite nanoparticles, different concentration of zeolite nanoparticles, to see how it's going to affect the membrane performance. So we have here is that nearly the composite, which is free of nanoparticles, for the rejection, percent rejection, it's like not letting the solute move from the feed solution to the draw solution. So it didn't change with the addition, nearly didn't change with the addition of the nanoparticles, while the water flux increased. The quantity of water that moved from the feed solution to the draw solution increased by like 3 times at 0.6 nano particles. For the results of the solute flux, so we used different types of draw solution. We used sodium chloride, different concentration, and magnesium chloride. And for the solute flux, we had an increase when we use the active layer. That's the active layer facing the draw solution, and regarding the active layer facing the feed solution. So if the active layer is facing the draw solution, we have solute flux, which is the solute itself moving from the draw solution to the feed solution. So it decreased when we have the active layer in front of the fresh water, or the feed water, sorry. While for the nano particles, we had it higher when we had it in the active layer facing the draw solution. So we had the problem is that the solute itself, we are losing it. The solute can be, as we have talked about, it can be a fertilizer that we don't want to lose it. It's going to go back for the irrigation plant or whatever. Or in some cases, they add some, there's some applications now is that they make like forward osmosis bags for humanitarian applications, or for if you are traveling in camping, where you can put like a bag filled with sucrose or whatever into the solution, into the water, and it draws the water from the river or whatever, clean water, and you get it and you can drink it. So we don't want to lose it. It's expensive. It gets to be recycled again, and all of this. So we don't want to lose it. So we get like if the active layer is facing the draw solution with the nano particles embedded into the membrane, we get to lose it in this case. But if we have the active layer facing the feed water, we can keep it a lot. Regarding the specific reverse diffusion, is that the solute itself into the feed, it's moving into the draw solution. That's what we don't want to do. Also, we don't want, like, if there's any contaminants in the feed solution, if there is salt and anything, we don't want to have it. We don't want to move to our draw solutions that we are going to use. So we didn't get any difference between when we had it facing the draw solution, or when we had it facing when we had it facing the draw solution, it was higher, it was moving higher than when it was facing the fresh water. And again, it was the same for the nano material. When it was doped with nano material, it had nearly the same values. And again, we can see that the different draw solutions that we are using, different concentration, will have some effect on the specific reverse diffusion in this case. When we are talking about the power, we know that the forward osmosis consumes much less power than the reverse osmosis. But again, we compared the power used either for the draw solution for different seawater salinity, when we were using the different type of draw solution. So we had an increased power when we were using the magnesium chloride solution, because of course the magnesium chloride solution had higher and much higher viscosity when used at small concentration compared with even with the sodium chloride. So you are consuming much water. And again, for the power consumption, when we were using it for the feed water, again, it was power consumption much higher for the pump. But again, it's still very much power consumption when it compares to the reverse osmosis. The different, we are going now to move to the second part, which is how we are going to use, after we made the membrane and everything, how we are going to use it or try to use it with in the application of making water. So if we have here, for instance, the saline or brackish water, which is fed here, so that's the feed water, and we are getting here some solution, concentrated fertilizer. When we add the fertilizer with certain concentration, so it will increase the osmotic pressure of the solution, and we pump it from here, from the top. So both of the solution will move counter current to each other, and water will move from the feed solution to the concentrated fertilizer solution. So we are going to gain some water. You have pointer. All right. Thanks. Sorry? Restart. Rewind. Rewind.
The next BioVision, inshallah.
So if we are, I'm sure it's working. Can you see it?
We know what you mean, Dr. Ash. Go ahead.
How I'm using it? What is it?
We feel you. Please continue.
So if we are going to have our concentrated solution, concentrated fertilizer, counter currently moving, so we are going to get more water from the saline water, and at the same time, we are going to increase the brine concentration, which can be used further, like Dr. Ashraf, my colleague, said previously, for growing or feeding Artemia. Also, we are going to use it to treat agricultural wastewater. Of course, agricultural wastewater after being treated to remove any harmful pathogens. So we are going to get the agricultural wastewater, add some fertilizer on it. So we are going to increase its osmotic pressure, move it. So we are going to add some fertilizer on the agricultural wastewater to increase its osmotic pressure and pass it into the forward osmosis unit or forward osmosis cell, and get some water from the brackish or from seawater or whatever, saline water, and again increase the content or increase the water that we are gaining or getting instead of using only the quantity in the agricultural wastewater. The third part that we can test it is use it with conventional RO. So RO, it's energy scavenger. It uses a lot of energy. It's very expensive. So we get like treated water you can drink. But if you are getting brine, which is very concentrated, instead of injecting it into the water and causing some environmental problem with it, you are going to pass it again against some feed solution or any agricultural waste and get some water and return it back to the RO. So instead of injecting it, you are getting water from here, from this concentrated waste, and then injecting it again into the RO, so you are getting again the treated water from it and the brine. You are doing a closed loop. While this concentrated waste, you can be like treated in zero liquid discharge or any type. It depends on the type of waste you have it here. So what the expected outcome? I'm not sure about the figures, but what we hope is a reduction of the cost of desalinated water, decreasing the cost of desalination system. Of course, you are not going to use a big high pressure pump, just some small pumps just for passing the liquid. lowering the operating cost. Again, the pumps will not use a lot of power, a lot of energy. Enhancing the supplementary irrigation by providing treated water to increase the variety of crops. Like we were discussing in the morning, is that you can change the way or change the type of crops you are using. If for instance, in the northern coast where they are growing barley, depending on the rain, you can add a little bit of water and grow wheat instead. And again, improve or increase the public awareness of the problem of water scarcity and importance of desalination through applying educational and training system through our unit. Yeah. Previous, yeah. No. At the end, I would like to thank our team in Alexandria University, Professor Abdulaziz Konsowa, the Professor of Environmental Engineering and the Dean of the Faculty, Dr. Dina Gayar, Dr. Manal Laofi, Engineer Asma, and Engineer Ali Ismail. Thank you. Very short.
Only 50 minutes. Okay, so I think now we got an overview about the type of research we are doing in this TriNex or Water-Energy-Food project that I mentioned before. And to conclude this part, I go back to only one slide here, which is this one, if you remember. This slide shows you the model itself. Just to conclude here, this is a part that we are doing together with the American University in Cairo, forward osmosis, testing different fertilizers. Here is the part that Cairo University presented, used Artemia for different types of fish, but was the main focus here on the type of products we're going to produce here, and also using saline water. So, and also Alexandria is focusing mainly on the type of membrane that's going to be developed, but hopefully, and also Heliopolis University is developing various models of using aquaponic in their research. This is an overview of the TriNex, and I think we will have quite some time for questions because we started half an hour late, and then we will get 1 hour. Okay. No, thank you, of course, but we will get first some questions. No? Yes, please. So please introduce your name and the question. Yes, your name, your position, your question, and the person you would like to get answer from him or here.
Okay, my name is Ramzi. I'm a sustainability practitioner. And my question may be evolved out of my lack of knowledge in this area, but specifically about water. I'm referring to a technology that is 2,000 years old, designed, patented, blueprinted, tested by the Roman Empire. The region of North Africa was the breadbasket of Europe, and they harvested rainwater. Where is this today? I mean, all I can see is archaeological evidence of cisterns.
The Roman wells you said? I didn't get that.
The Roman Empire.
Yeah, but the type of technology that you mentioned.
Gathering and capturing rainwater,
Harvesting
rainwater into cisterns. And the only evidence I find now is the archaeological evidence scattered all through northern Africa. Has this idea just died? I mean, is it feasible today? Is it in any way useful to us?
I will give part, but if any of the panel would like to reply, it's out of the scope, but I don't mind. As water people, we should be able to give also a feedback. We have some experts here, Dr. Muhammad Suleiman, he is the expert in this area. But my personal opinion, yes, if you mean the wells, the Roman wells, to harvest the rainfall and store them, yes, we do have some historical places. I think the rainfall as a hydrologist is moving. I mean, we don't have the rain in the same places. We have the problem mainly in other places, but I think we have also the experts here to provide. But what I mentioned in the early slides of my presentation, that rain harvest is the solution for the Nile Basin. It's not this type of rain harvest. We are talking about huge amount of water. I was mentioning 2,000 billion cubic meter is the rainfall on the Nile Basin countries, and this is not the technology. We are talking about harvesting and reorienting the rainfall to move it from the type of green water to blue water and to reach Ethiopia, Egypt, and other countries. So this is the stores that you're talking about is under the ground to be used locally and not transporting the water to other place. So this is a completely different issue. But I give the microphone to my colleague, Dr. Mohammed. He would like to comment on that. I don't know whether Dr. Hani would like to interfere.
Yeah.
Okay. Good.
Mohammed Sulaiman, Director of the Coastal Research Institute and also Professor at the National Water Research Center. Actually, still Roman type of harvesting is still working up to now, and even we introduced some of the new technologies for the valleys there, the wadis system, by constructing some of the harvesting techniques, underground dams and underground reservoir, they called Kestern, زي صهاريج يعني تحت and this already in the north coast already developed ranging from 500 meter up to 1,000. Of course, it is small due to that is not a frequent rain or the blue period, but it is for sustainability there is working. So the Bedouin and other remote inhabitants are living there are depends in the old, still existing Roman type of wells, and also the new constructed harvesting in this region, and still, but the scale is small, not as the Professor Hani mentioned. The upper Nile is we're talking about billions,
Huge
not,
amount.
yeah.
Thank you very much, Dr. Hani Nokrashi.
Thank you. My name is Hani Nokrashi. I have several questions. The first question is the irrigation water, which is used here, is coming from PV panels. So you have the energy during the day. In the night, you don't have energy. Do you stop the desalination unit during the night and start it again in the day? So this is the first question. The second question, you have some sorts of fish or fish food being grown there, so you have to control the salinity exactly, so that it will not be harmed. We did not see figures of this. Mm-hmm. Is it everything under control? Because if you use it on the Mediterranean Sea, you have starting with a certain salinity, about 25 or 30,000 parts per million. And if you have it in the Red Sea, it is much higher, or in the Gulf of Aqaba, still higher. And the third question is to Professor Rasha El-Kholi. One of the pictures which you presented to us, we have seen fish in a container, and it looked all dead fish. I understood that you are growing the fish.
The experiment was.
So
we were testing killing the fish.
Yeah. Okay. These are the questions. Thank you.
Thank you very much for the three interesting questions. I think the first one is mine. The fish goes to Dr. Ashraf, and the dead fish goes to Dr. Rash. So the part, of course, you know, I'm not an energy expert, but using PV panels, of course, during the day and storing and batteries for this experiment that I showed here. We do have batteries, but I don't think for this experiment we do have batteries to store, and we calculated the 10 kilowatt to supply this pilot unit and this prototype with the required energy 24 hours or to cover the demand. But we assume at a certain day when we are ready to implement it in the reality, it's enough to desalinate the water during the daytime, because first, you don't need to irrigate every day. Second, you don't need to irrigate 24 hours. The main problems here, I don't think it's the PV panels. The main problems is getting the right concentration of the fertilizers to go directly to the irrigation, because what we produce is water with the high concentration of fertilizers. What we used is ammonium sulfate in the last experiment, and I send you today some publications if you're interested. So, and how to get the water diluted so that the plant itself can tolerate it, this is really the challenge we are having now. But of course, I fully agree, you are the energy expert. PV panels, they really will help us only during, not even the whole day, but during the sunrise time. Regarding the salinity required to be adapted for the fish, I leave this for Dr. Ashraf Sallouma.
We talk here about zero exchange system. I talked about aquaponic, saline aquaponic, and this is zero exchange. So the salinity, the control of the salinity is not problem. This is the zero exchange. And the second system is...
Could you please explain more what is zero exchange for the audience who are not experts?
This is recycling system that the water from the fish tank, the effluent, which contain high level of nutrient and especially ammonia, it will be go to the biological filter to convert it to NO3, that the nitrate, that the bed, the plant will be it's fertilizer for the plant, and it will be recycled and returned for the fish tank again. So this is zero exchange. So the control of the salinity is not problem. And the second system is bifloc, and this is the same. It's one of zero exchange system also. This is we called it this system is we treat the water, treat the ammonia within the system by activate heterotrophic bacteria that we add to this bacteria to activate carbon source, and the bacteria consumes the carbon source and takes the ammonia, and we solve the problem, and also the bacteria consumed by the fish. So we treat the treatment within the system. And this is also zero exchange, because we solve the problem with the ammonia, so we don't need to remove the water or exchange the water. And our system also, it's not only for this brew type. I mean that here we need the system to be zero waste. But also we can use, in the desert, we can use directly the saline water from the well for zero exchange also. I mean that we talked about this prototype, but also we can use directly saline water, not from desalination unit.
Okay. Just I need to add to this, because this was a long discussion in our meeting at Cairo University to design the whole concept. I mean, how to bring different researchers in Egypt from different universities to collaborate together. So we were doing some assumptions that this desalination unit will produce fertilizers with a certain concentration and brine with the other concentration. And we were making some assumptions, say, okay, assuming that the prime concentration, I don't know, 30,000 ppm, then Cairo should be, Alexandria should be testing starting from 30,000 and 35 and 40,000, etc., to do some different scenarios for each researcher, and then hopefully at the end we will be able to couple all these research together in order to have this model that I showed, and then test it and optimize it as one single unit. Now to the dead fish.
Well, starting first with the question about the energy, that the amount of energy needed for the desalination, the pumps and the operation is enough for the morning, meaning that this is a closed loop, and the amount of water that's desalinated stays in the system. So there is no need for the energy in the afternoon, just small part for the pumping and the aeration and the degassing of the system. And part of this energy in the morning, which is more than that's needed, is pumped to the network. That's part of the energy. As for the fish, as I showed in the picture, that the system is completed to the phase of the construction. There is no real fish so far, so this is not our dead fish. But I assume this is the fish at the time they are getting it out of the tanks. So there are nets getting the fish out, and it's quite calculated the amount of energy that the amount of fish that will be in this circular cylinder tanks, and the amount of production that's getting out, and we actually in this phase we're looking at the phase of using getting salt from the brine coming out of the system. So we're not yet operating. We are in the construction phase. End of May will be the start of the system. Thank you.
Good. Any more? Yes, please.
My name is Salif Diop. I'm from Senegal. Just to ask, for the time being,
From which country?
I'm from Senegal.
Senegal.
Myself.
Okay.
For the time being, it's a prototype. It's a project. Huh?
Yes.
Lab testing and all those things. Because in some other areas, even in our countries, we are testing we are not testing. We are moving into the nexus, water, energy, and food. Mm-hmm. But it's really for trying to use as much as efficiency water, using low energy with low cost, and then getting food. That's the objective. And we've been doing it. I mean, and it works. What I'm wondering is the cost of this in terms of cost, because you haven't given any figures. How much it's really cost, because we're trying really to reduce the cost of all this, because if we do all this and if it's very expensive, you see the value of what of course, we have groundwater, which is fresh, and we can extract and use mixed energy. We are not using not only PVs, but also the wind to extract the water, and
yes,
then
sure.
Bring to the food. And the water we are using is really drip agriculture. It's a drop, each drop, because trying to really make use of all this to make it sustainable, of course, for the future. What I'm wondering is, number one, the cost. Number two, how do you think that this could be sustained, and investment which will be needed in the future to make it extensive, and then how it will be translated into the reality. That's just what I'm just questioning, yeah. Okay. Because of course we can exchange information.
Sure.
And,
I think we'll be very happy to collaborate. Anyone would like to give feedback?
I would like to add just one part, that was part of the plan, not just to put the things running on the ground, but to look for the coming step. And it's not just for the cost analysis, but we're rather looking for a business model, how this could be implemented, or the environmental, social, money-wise aspects involved, and how this could be sustained. Who would fund this? Because putting renewable energy is costly. So who would fund this? How this can be implemented? Who would support this? And yes, we're using every drop if it's a closed system and there is a multi-function of the system. We're making the maximum use. But this, the end product should not be that, yes, we're producing this or we're having this, but the end product is that we are presenting the business model for what we are doing on the ground. And of course, we'd be very pleased to have other experiences involved and building on similar cases that has been using any or relevant issues to what we're doing. Thank you.
Okay, Dr. Ashraf.
We talked here also about the community, that it's far from the sources for fresh water. I mean the coastal area or desert area, that there is no resource, that the main resource will be seawater or the underground water with salinity. So the first, we don't have option. So we don't talk about the cost in this case.
Okay. I would like also to add that our basic assumption, as I mentioned in my slides, that reducing the energy used for desalination to the minimum, because big part of the cost of the desalination is the cost of the energy. So our experiment, if you remember the charts, that the forward osmosis technology that we're using is using really less than 30% of the energy used by RO. So we are assuming that the cost of energy will drop by 60, 70%, and this is our assumption. So by all means, the process we are following will never be more expensive than the RO because of the energy part. And what we always forget is to put the cost for the negative environmental impact. I mean, if we are talking here about using the brine for producing food, so this is an added value that was not in any desalination technology before, of course, assuming that this will be working perfect. And in addition to preventing any environmental impact with its adverse impact on the health, and this is also a kind of cost that we need to consider in our business model, as Dr. Rasha mentioned. And this is a discussion right now to involve people from the School of Business or faculties of business to make the assessment. And since we are talking about sustainability, so it's not only about environment, money, and economy, but it's also about society. What is the society acceptance of that? We would like to see farmers having this model as a model that can be built using an Egyptian technicians and Egyptian, not necessarily farmers, but at least Egyptian engineers. So these are the factors we are considering. And as you see that we are considering the pillars of society, economy, and environment in order to be sustainable. And this was your second part of the question. Other comments? Or no? There is, yes, Dr. Hani, and then we take this one. So you want to close? Oh, really? Why didn't you close the previous session now? Yes.
Excellent work. I'd like to congratulate you for this. Really, you have touched two issues to make all this research and all this production of food and water for planting without fossil energy. This is a very big achievement. Congratulations for this too. And also the very big idea to use the brine to make food. It's a brilliant idea. Thank you for that. We all see that it is at the beginning of the research. Beginning of the research, we cannot assume that everything is going 100% as we look. I hope that you succeed in this. And the third one, what you have achieved, is the cooperation between the researchers, and that is at the end an Egyptian research, not just that the Egyptian researchers are working as help people for the European and American and Japanese one. Thank you very much for it.
Thank you very much. Thank you very much, Dr. Hani Norashi. I think you are a well-known figure, not only in Egypt, but for us in Germany, you are a role model. So we always try to follow what you are doing in Germany in order to be one day at the same level of your experience and know-how. And I know that now you are one of the advisors of the president, and helping a lot in the country. So we're trying to do the same. And all what you said, it's not to me, and I think it goes to the whole team. It goes to Dr. Rasha, Dr. Yahya, and Dr. Ashraf. Not only those people, we have more than 30, 40 people working in this project. Very, very disciplined, very nice team, and I think they are doing perfect. And the challenge, as you said, is to bring researchers together. Really, you bring researchers and divide the job between them, and each one is doing one piece of the puzzle. And hopefully one day when you bring all these puzzles together, then you have the full picture. And then you have an Egyptian technology to use the sun and produce food for the Egyptians and also the Africans and also the Mediterranean countries, the people who really deserve a lot from us. Thank you very much. I enjoyed the session. I enjoyed the discussion with you. And we will be available. We have a booth for the project downstairs. Please visit it. If you need contact information, if you would like to join the summer school or our final conference that I will surprise Dr. Abdelaziz that he will be organizing in Alexandria. And we thank you very much and see you next BioVision, inshallah.